And do you record it from here or?
The mic is up there. I'm recording just on the computer, so I can just
Okay.
post
Then
them.
there is a record option here also.
Yeah, those ones I like never know where they go.
They ask you at the end, but you should be careful. All the
Yeah.
ones.
Exactly.
Yeah.
That's and I am you know prone to errors. So yeah, welcome everyone. This is I guess HWRS 640. The title is Computational Methods for Data-Driven Earth Science. This is the first time I'm teaching this class. It is something I'm developing. So, and because we have, it's a small group, it's a higher level class, I really do want it to be, collaborative and like, this course isn't for me to just spew information at you. It's also for you to get stuff out of. We'll talk about what I have planned for the syllabus. We can go off syllabus as well, like we can pivot, do different things, and that's totally fine. It's just one of those, like, you got to like submit the syllabus for the university to approve the course, but in no hard terms. I mean, there are things that I really do think you should learn in this class, but if there are things for your research or for anything that you're really interested in with, respect to the overall content of the course, please let me know. Let's talk about it. Let's keep it somewhat informal. And with that, like we're talking earth science. So like most people get into earth science because they want to go out in the field, they want to do go chip some rocks or take samples, and then you get into it and you go, oh, I'm just at a computer all day, right? Like that's just the nature of like doing science at this point in time. And I think in a lot of ways, with various forms of earth science, hydrology, atmospheric science, geology, etc., we don't give people the tools to do rigorous computational science. And so that's kind of what I want to address in this class, is give you some of the fundamentals, build up, so that it's not like, I feel like a lot of people just end up like, oh, I have to learn programming on my own, I have to learn these various methods, and I go and take a class in like, applied math, and none of the data sets are like the same as my data sets. So applying the methods becomes like, a thing that you all have to learn. So that's kind of what the bridge that I want to make for this class. That kind of, I don't know, does that jive with all of your experiences and stuff? So again, what the sort of general thesis or the motivating factor is, like, data and computation have changed the way that we understand the Earth system. It's not just people going out and like looking at things and taking these very small samples and trying to make complex inferences from them, but more and more, we're just taking these huge amounts of data. We're working collaboratively on very large and complex code bases that either simulate or analyze the Earth system. And I think, again, this idea of bringing rigor to the computation part, that's not just like a numerical methods, but also like the data analysis part, the statistics and things, and kind of bringing it all together into one spot. So just to really sort of get into what we're going to talk about for the first little bit of this class is computer architecture and understanding, like, sort of fundamentally, like, what are the things that you should be thinking about when you are building large data analysis, whether it's a big simulation, a big data processing, machine learning, etc. These are all things that if you sort of know how to work with the computer better, you can be more effective, right? And so computers obviously have gotten so much better, over the last 50 years or so. And there are changes that are going on in computer architectures, like, some of you may have you've heard of or used things like GPUs or TPUs or other sorts of accelerator cards. The same with like parallel processing has become more and more of a thing. So this is sort of the classic example of speed of computers getting faster and faster over time, which is like Moore's law, which is like roughly the speed of computers or the transistor count. And we'll talk a little bit about more of the nitty gritty of like computer architecture on Friday, but they roughly doubles every few years. And while this is sort of slowing down in terms of sort of the classic Moore's law, it's still, computers are still getting better and better. And that relates to things like like I was saying, the multi-core machines, memory capacity, storage speeds, and all of that lets us do more science. So understanding how to do some of that and hopefully getting a little bit more of an overview of what you can do with computation will be helpful. And then on the other side, of course, is the data. So if we have more capacity to process stuff, we want more data. And so data is growing at this increasing rate. So this is just a little figure showing growth of Earth science data. I believe this was, if I remember correctly, this was like a NASA thing, but you can see we're talking about hundreds of thousands of terabytes in terms of like data storage, and processing that requires specialized knowledge in computing and programming stuff. So again, it's a situation where these technical skills increasingly are the way that you advance science rather than just thinking real hard, right? Like you can think about a hypothesis, but if you don't know how to process these huge amounts of data or anything, you can't answer the questions you're interested in or the advances you want to make. So that's really where I think a huge amount of progress is left to be made. And then the other thing that I just wanted to mention, because we will at some point, and we'll talk about this in the syllabus stuff, the data sets are not necessarily, it's not evenly distributed. Like you see the orange here is like model data, so climate model data, reanalysis, and things like that are huge. And then satellite and radar remote sense data is also the other huge part. There is a tiny little sliver of what they have as in situ or other, which is like field observations. And it looks small, but that data is obviously, super valuable, arguably per data point more valuable than a model data point. So, and it's working with them together is also very challenging to think about. So that's one other thing that we'll sort of talk about. So the purpose of this course, as I've mentioned, I want you to feel like you're this person here at the end of the class where you're just like, you're at your computer, you're vibing, you're able to do the research that you want to do, build the pipelines and stuff. And be able to work across a wide range of problems, because I think, the Earth system is totally interconnected. We all have our little niche, but being able to like look at what someone else has for a data set and be like, oh, I could use that. Super valuable as well, right? And I think a lot of times, you go and someone's like, oh, I've got this data, and you go and look at it and go, garbage. It's formatted weird or whatever. And I don't know how to get it into the algorithms or the modeling processes that I really want. So gonna do a total pivot here. We're gonna start talking about computers. So my pop quiz is, how far do you think light moves in 1 nanosecond?
I used to know this. Peter used.
Ah,
It's about,
I had to look it up.
it's about this far, I remember. Somewhere in this.
Does anyone else have any other
distance.
guesses?
A lot more than
A lot more or a lot less? Let's poll the audience here.
It's 3 times 10 to the 8 meters per second.
Okay. Oh man, if you're gonna do this in your head, you're just I'll sign the form. You can. Any other thoughts?
Yeah, I think it's gonna be a lot more too.
One more second.
It's gonna be on the, I can't remember specifically, I think it's on the order of about a meter,
You are
less.
quite close. It's about 12 inches. So about a little bit shorter than you said, but
That's crazy. I thought it would be like,
yeah. And so this is why I think this is an interesting starting point for talking about computation. And this was like, Grace Hopper, you should, in your free time, go and read about her work. She was an early computer scientist. She's the first person who built a compiler. For any of you that know about or have heard of compilers, she was the first person to build a high-level programming language. If any of you have heard of COBOL, which is still used by a lot of like banks and stuff with legacy systems. You can make a shitload of money doing COBOL programming, but you got to work in weird stuffy banks and stuff. And she also is the person who coined the term computer bug, because she was working on a system like this, where it's not like, today it's all, nothing moves in your computer anymore, but they used to have tapes and, vacuum tubes and stuff, and the computer wasn't working. And she went and was trying to investigate why, and there was a bug that had like broken one of the pieces of the computer, and that's where the term computer bug comes from. So super fascinating history, but this was a rhetorical device that she often used even back in the 40s and 50s to talk about, it's surprising, a lot of people would think it would be much further, but light is the fundamental speed limit of the universe. So we're really, when we're talking about modern computers, we're bumping up against that. So modern CPUs, the thing that makes your computer, compute, run at about 4 gigahertz at the top end, which is about 25 nanoseconds per cycle, which is like doing one thing, one operation, I'm going to copy memory from this place to this place, or I'm going to do an add between these 2 data points. And so, again, we're really bumping up against this. So my next question is, how far do you think light travels in 1 CPU second or 1 cycle?
wait, so it's a 0.25 nanosecond for the CPU.
Yeah. Yeah, so we're talking about, and this is light. This is like the fastest you can possibly get. It's about a couple centimeters roughly.
7
What's that?
like 7 centimeters.
Yeah.
Because 1 nanometer was like 12 inches, 30 centimeters. So we divide by 4. Like,
Exactly. Yep. So that's like what we're bumping up against. We're like, when you think about what you're doing with data processing, it's actually very like impressive feat of engineering. And also like, it's hard to go much beyond what we're already doing, right? Your CPU is, in most of your laptops, is probably about this big. So when you're doing this, you can hit, the electronic signals travel a little bit slower, but roughly the speed of light. And so this is what I want you to just be. I think it's worth being in awe of this stuff, right? It's kind of fun to think about, and we don't often get to do that. So now we can talk about course organization. I have a couple things I want to do. I'm actually going to go the other way. I think it would be good to do introductions. I know many of the people who are going to be in this class, and there will be more eventually, but I guess we'll have to do a second round of introductions. But so yeah, I would like to just do some introductions, talk about what you want to learn, and then I can take you through what I kind of had as an idea, and then of course we can talk about organizational boring stuff. So yeah, with that, I of course am Andrew. Please feel free to just call me Andrew or Dr. Bennett, whatever you prefer. Doesn't matter to me either way. I'm an assistant professor in this department. I'm primarily a hydrologist. My background is in computational physics and scientific software engineering, and then I went to grad school for hydrology, sort of because I was like, oh, I didn't know you could do stuff like that. And now primarily my research is focused on integrating machine learning, deep learning into traditional physics-based hydrologic models, primarily focused on the physics rather than like chemistry or water quality stuff. I have dabbled a little bit with some atmospheric stuff. Quite a bit of my work is sort of at the interface between the land and the atmosphere. And I would like to bring a little bit of that in. This class is not going to be just hydrology. There will be other data sets that we work with, ocean data sets, atmospheric data sets. We'll have some opportunities for you to bring in your own data sets. We'll talk about that with the sort of final project. But that's sort of my background and perspective on this. So yeah, let's introduce everyone. Do we just want to go around this way?
Sure.
My name is Jack. I did my undergrad in this department. I just finished last semester, and now I'm a master's student here doing the accelerated master's program. And I work with Dr. Bogwo. He's kind of actually heading towards the same, integrating machine learning into the physics models, but he's coming at it from more of like I think you're coming at it really from like a data standpoint right now, and he's coming at it from like the PDE standpoint, but you guys are kind of converging. So I thought I just took his class last semester, and I really wanted to take this one. I saw it, and it seemed very applied.
Yeah, I think it's a good one too. I would also say, yeah, the other thing I guess I didn't say is I work at the much larger scale than like Bo. So I work at like landscape to continental scale.
Yeah,
so.
and he works like microphysics. Yeah. So like, for instance, right now, my project is looking at like, you guys are familiar with the PFAS chemical, the forever chemical, looking at partitioning through membranes in plants and looking at like molecular dynamics.
I'm Roz. I'm over on the Atmos side of things. I am in my second semester of my master's. I did get my undergrad here at this department last year and was a part of the accelerated master's program. So hopefully in 12 months, I will be hooded. Fingers crossed.
We love to see it.
Fingers crossed, everything works out. In 12 months, I will be on towards PhD, but we will see if that happens in 12 months. My research is with YOD. I'm doing stuff with a couple of data sets, ERA5 reanalysis, large scale data set, as well as the GridRAD Severe, which is a radar-based data set, although that hasn't quite worked out in the way that we were hoping to apply it, but that's all good, as well as the PRISM. Yeah, as well as the PRISM data set, which is a precipitation it's kind of like a precipitation reanalysis data set. It's a little weird how they do it. It's a combination of both radar model and direct in situ measurements all compiled into one data set to try and get a more holistic image of what all of the models are saying that rain should be. Now, taking that as truth, using that as a background to try and see if we can do some machine learning to pull out different kind of modes of precipitation here in the Tucson region. It's going.
I mean, precipitation here is challenging.
So difficult.
Hi,
As
everyone.
Jose,
Yeah, I'm working on that very quick stuff. My name is Hossein. I'm a PhD student. I'm in third year. I'm working on the downscaling project with Ali Barangi and Andrew. We all have some problems also with precipitation, but other variables is much more easier. And I took this class because it was very similar to my current work that I'm doing, because I was tired from downloading each time new data sets, doing the pre-processing, and each data set has a different, sometimes some part is very similar to each other, but some parts, the way that you should download the data and these things completely different. And that was really pain for me. And I think it's for everyone in hydrology part. That's why I'm doing also my internship for a company that we are working on something like this. We are making a package now that we can just go inside the package. And this is a goal. This is a part of the bigger project that we are making. But in this package, for example, we have different things. We have for the downloading data, we can say, I need timers, I need this variable, this time period, this range. You don't care about anything else. Everything will be in the background, and the package will send you the final code, and we can just run it down with installing all the packages by themselves and everything else. And also, we are doing the same library for the pre-processing, because sometimes data has a different time periods, temporal resolution, different levels, and different variables, and a lot of other things. And that was also always a problem to do. So also, this package included a pre-processing that's we are connected, downloading to the package, the pre-processing, and they can make the data ready for you to run the machine learning or whatever else you like to prepare the data for. So I can show you later some framework of that package, but I think that was the reason that I took that. I'm happy that maybe I can get some advice from you guys during the semester to improve it, and yeah.
and they make a good final project, which we'll talk about after this.
Hi everyone, I am Wani. I am from Bangladesh, and I did my undergrad in Bangladesh from Bangladesh University of Engineering and Technology. So my background was in water resources engineering. So initially it was within the civil department, but later then they pull it out as a specialized department, and the structure is all mine. So my undergrad thesis was more of like river hydromorphological modeling. I did that with the HEPRAS model. So as my country is a deltaic country, so modeling this sediment is more challenging there. Then I did my master's also in Bangladesh. I did it in climate modeling and risk management, and there I mostly designed the hydrological part. So with the SWOT model, I modeled the stream flow for the upper Meghna Basin. At the same time, I was a research assistant during my master's times, and I was involved in a Netherlands-based project, which was called the Global Climate Adaptation, and they were aiming to provide like nature-based solutions to the southern side of our country, and then I came here to the hydrology department for my PhD, and right now I am working with GoU and Ali Barangi, mostly working on the weather modeling. So currently I'm working on the GoMP model.
Awesome.
And I have chosen this model because during my master's, I used a fully deep learning model without any physics to model the catchment stream flow.
Hmm.
But later then I found that actually the next paradigm is to infuse the physics with the deep learning model and to interpret how the deep learning model or the machine learning model is getting those answers. So then I thought I should dig more up to, to this.
Yeah, we will talk about that.
Yeah, I'm brand new to the university.
Welcome.
Welcome.
So I started as a scientist or postdoctoral at School of Natural Resources, and my background is in hydrology and hydraulics, mostly in hydraulic modeling. And for my research, I was using mostly remote sensing data to study river changes, and I was implementing some machine learning, deep learning algorithm, and I use all those algorithms by myself. So I wanted to have some kind of a structure. That's why I thought this class will be really useful for me. And for my current research, I will be working on studying the impact of worm. It is like unengineered small dams that are built like Honeybee ago across Southwest United States to control erosion. So I was working on that project, and we are also planning to use some deep learning to study that one. So I thought this class will be really useful. And thank you so much for letting me in.
Oh, of course, of course.
I have no idea how to enroll in class.
Well, either way, we'll figure it out. You're always welcome, of course. Are you looking at like infiltration rates with the berms? Or?
Yeah, that was the plan. Like we will be looking at how worm will help us like controlling erosion and how it will impact the overall water quality.
Cool.
And also the response of vegetation forms and how they are responding with time as well.
So are you looking at like large watersheds as well as very small ones with the berms?
Worms are small, but we wanted to look at all of the worms, existing worms in one watershed.
And those are man-made.
Yeah,
Yeah,
long
okay.
time ago. I'm still learning about the history.
Yeah, we actually worked on a berm. I went into his office hours one time. I was like, hey, I'm doing some work for the law school. Someone had built a berm on their property, and we were trying to compute the volume. They actually got back to us. ADWR was like, "Who did this? This is awesome."
Oh, hell yeah,
Yeah,
that's
so,
cool.
yeah.
Yeah, I'm just learning about it, and yeah, before coming here, I worked as a postdoc at the University of Nebraska for 1 year, and before that, I worked with Tetra Tech as a hydraulic engineer for 2 years after I graduated from. And my PhD and master's is from the University of New Mexico.
Do you know Roy?
Roy?
Yeah.
Yes.
Oh, okay.
We
Cool.
were collaborating on one project at the end before I leave.
Okay. Yeah, he got his PhD here.
Oh.
You know, Isaiah.
Yeah, he told me about
Sorry.
Okay, awesome. Well, nice to either meet you all or hear your what you're up to. So I'd like to go over the syllabus at this point. Unfortunately, we have to do this, but it also provides an opportunity to talk about what's in the class. The first thing that I'm going to ask is office hours. I want them to be available to you. This is, we're here Monday, Wednesday, Friday. I think it generally makes sense to do office hours on one of the days that's off the class. Are you all, would that be a good starting point? I really don't know how assignments or homeworks and stuff are going to go in this class. I'll be pretty flexible with things. I mean, you're all motivated. You're all, in grad school. So I don't treat this necessarily like I would strictly as an undergrad class. Would Mondays sometime in the afternoon generally work for folks? What other commitments do you all have?
Mondays generally work fine for me, but I'm not sure about everyone else.
So
Same.
So I have a meeting on Monday from 2 p.m. to 4 p.m. So other than that block, I'm free.
Okay. We could do right after class on Mondays or something like that.
That'd be fun with me. So
I'll tentatively set that, but I know we still have, I think, 4 other students that work out for this week.
it's gonna be hilarious. They're only, the only day they can't do is exactly Monday.
It happens. You know, that's why I say, you know, TBD, we'll figure it out. It usually takes a week.
They never join us.
Yeah.
Right, yeah.
They're like, we can't do Mondays. Move it. It never appeared. It's like, okay.
I will set that. I mean, but also, you know, it's a small class. I actually finally have a chill semester. So, you know, you can always reach out via email and stuff, for anything in the class or for your, you know, other research things. If you're like, we kind of talked about this, could you, you know, see if you have any advice? I'm happy to try to help. Again, this is a course aimed at helping people do research. Okay, so the core prerequisite of this class is having some programming skills, which I assume, based on what I've heard from you all, you are all pretty good with. We will do everything, I believe, in Python at this point, if you're okay with that. You're allowed to turn in assignments that are done with other programming languages, but I won't be able to verify your code, probably. I might be able to. I do know other programming languages, but no guarantees. And then I realized I totally forgot every semester you have to like go in and like approve the course D2L thing or whatever, Brightspace. So I did that today and it should come out to you all. I will put the syllabus on it, but unless you're really hankering for being on Brightspace or D2L, I would prefer to put everything on GitHub. That way the course materials just become a permanent thing. Like after the semester ends, you can go back and look at it, you can download it, you can remix it, you can do whatever, share it with your friends, they'll think you're cool. Does anyone have a problem with that? Okay.
No, that's good.
Okay. So I'll run it that way. I did set up a course website this morning for that, and I'll distribute that to you all. And that will be where stuff lives. As far as computing stuff goes, this course is a mix of lecture and hands-on stuff. So generally speaking, if you have a portable laptop, it's probably good to bring it to class, generally speaking. For the first bit, we're going to be, which I'll get into, we won't be doing too much of it in class, but definitely probably the last 2/3-ish will be much more hands-on. And well, you don't have to run all the code with me. It's sometimes useful to play around with things. And so I like to do courses like this that way. We also will be covering some or a lot of deep learning stuff, which your laptops may not like especially much. So I will also provide a GitHub code space, which is a cloud-based computing environment. And then I'll also introduce you to Google Colab, which lets you use GPUs and stuff for free if you need that. The last thing I would say is if you don't already have an HPC account, a high performance computing account with the university, that's something that you all can request with your advisors and use, and you could use that space for this class, which also may be useful to you because a portion of the class will be focused on doing something researchy, so it ties into all of your Does that sound good? Does anyone have questions about that sort of aspect? I'm gonna be mostly freeform. I'm gonna let you all decide how to run the code, do the analysis and stuff, but I would like to provide you resources to be able to do it as well.
I just like the comment. I'm interested to see how you're going to teach us how to use Google Colab, because I tried to use that instead of using like the VS Code. And I remember just being really annoyed having to like load in my files every time I wanted to do anything.
Yeah, so I think when we do some of that stuff, there won't be, we'll talk about accessing cloud data sets where like on the computing cloud, not the atmosphere cloud. And so you won't, I'm hoping that I can pull this off. So you won't have to download stuff, you'll access it, pull it just directly over the network.
Okay.
We'll see if this actually works out.
Only one way to find out.
Are the assignments are related to each other to make something bigger, or just for practice for the final project?
Sorry, what was it?
The assignments that we are going to do, so are they related to each other, or they are like more practicing to get ready for something else?
I mean, there will be a mix. You know, some just like, well, let's just go into. So yeah, these are sort of the core fundamental course objectives. Is like understand the computational foundations. That way, when you're like trying to choose how to approach a new problem, you'll be able to do that effectively. We'll talk about some mathematical foundations that I think are really helpful for thinking about data analysis, machine learning, modeling, sort of just in case you haven't seen one or the other sort of fundamental stuff. Then we'll talk a lot about deep learning techniques and hybrid modeling. And then the last piece is those practical skills of like, yeah, I can tell you like how to develop a model, but how do you use it? And so those are the core pieces. The grades, you know, you get, I anticipate no one will lose 20% on class participation. We'll have, I said weekly, we'll see. I hope to give you your first assignment on Friday, but it'll be an easy one. And then the project is, again, going to be, the idea of the project is going to be sort of mid-semester, you will find a data set that you want to work with and do some sort of modeling or analysis with. I hope, or expect that most of it will be related to your research, but then you'll use some methodology from the course to put together, a little project report. Should not be too much of a lift. Grades are standard policy. I generally have the policy that we drop the lowest scored assignment, but again, I'm really not worried about this group. There's no final exam. It's going to be project presentations. It would be, I really don't know how you would do a final exam with the computational, like programming competition. That would be crazy.
You have 2 hours, make a new data set from the ground up.
Right,
Go.
yeah, exactly. It's like, no, I don't know how you do it. Someday I'll figure it out and the students will hate me. Please work together, collaborate. This is, right, you're all either, through grad school or in grad school, like collaboration is good. Work together on your homeworks. If you hit a bug or something, go for it. Also, feel free to use AI tools as you see fit. I am not going to be gatekeeping you with respect to that. And generally, if I can give you my advice on that, is only use them to the extent that you will understand what they produce. And my other general thought is there will be some like short answer writing assignments, and I would really prefer you don't use AI tools to generate your responses for that. Obviously, they're hard to detect, so I won't know if you do probably, unless it says as an AI chatbot, which sometimes the undergrad students still turn in. So again, just be judicious, that we're here to learn. So, and if you do want to learn how to use those types of tools to be more productive in research, we can talk about that, and use them ethically and so forth. Which leads us into, so the schedule of topics. So kind of this course is broken into 3-ish big segments. You could maybe make the argument for 4. So this week and next week, we're going to be talking about just computer stuff. So on Friday, I'll talk about computer architecture and how it relates to actually doing computation. Just some things that I think people should have in their head. We're not going to be super rigorous about it, but I think it's useful. And then next week, we'll talk about more sort of nuts and bolts, talking about parallel programming, how you actually set things up to do parallel programming, especially in Python and for data analysis. We won't be talking about like huge scale, like how you set up a climate model on a giant supercomputer. Although that will be a part of your first assignment, is to look into some of those machines and try to understand how they work. And then after that, we have our sort of math refresher, which is going to be the next 3 weeks. So to really understand modern numerical methods, modeling techniques, and deep learning, I think there are 3 topics that you really need to have at least be conversant in. So we're going to do a refresher on linear algebra, numerical methods, and statistics. We'll just do 1 week on each of those. Have you all taken courses in those areas?
It's been a few years since I did ODEs, but
Okay.
got asked ODEs.
Okay, yeah. So
Got it,
and I want to talk about them in relation to why they're applicable to earth sciences broadly. Yeah.
We actually did all this in Bo's class last semester. So
I kind of figured, but
yeah,
I didn't know he was teaching this last semester.
you guys should really get together. I think there was a lot.
We do talk a lot. We
looking
just generally don't talk about what we teach.
Yeah, that's fair.
So
He snuck into the syllabus and is like, I'm going to ruin this man's career.
That was I think it was very different ways approached.
And what we're going to also talk about is like how you use programming and software, like computation, to actually make use of these tools, hopefully in a slightly more applied way. And then after that, hopefully, did Bo talk about SVD?
Yes, singular value decomposition, and then basically the only thing we didn't really do was tensor we did this SVD.
Yeah.
And then also Dr. Winter went over that too.
Yeah.
In his class. And then we did not do dynamic mode.
Yeah, so dynamic mode is like one of the generalizations of the singular value decomposition. Which,
Gotcha. We definitely did backpropagation, gradient descent. And then we went over diffusion models. We never did them.
You will be doing them.
And CNNs, we never did them, but we understood the math behind CNNs and diffusion models and transformers. But we did use a lot of MLPs.
Yeah.
And then we did some operator learning as well.
So that comes back. So then the second packet is like the setup for, or I guess third packet is setup for fundamentals of machine learning, or how should you think about data to do machine learning. And so the singular value decomposition is fundamental to data analysis, and also just how you think about systems, like how you should think about does my data support this method versus that method? So we'll talk about some sort of more conceptual stuff there, and do some regression and how it's related to all of that stuff. And then we'll talk about optimization, just so that it relates back to your OD solvers and stuff. And then we get into the core of the machine learning stuff, which I will show you sort of the classic examples of some of these, but with MLPs, I'll talk about like channel mixing and different ways that information flows through the system, and CNNs and RNNs, thinking about different ways to set them up, because you might have heard of CNNs, but there's or convolutional neural networks, but there are different ways to set them up that, and I really will talk about it more in like an information flow and that type of perspective, which will hopefully be something that lets you go from like, I get the idea, to like, I could design something that is more effective than us, you know, your standard situation. And then we'll talk about transformers, which like they just work. I hate to say it, but they just work.
Just works.
Yeah. Yeah, I mean, they're the backbone of all of the large language model stuff, as I'm sure many of you know. So, but you got to know them, so we'll do it. And we'll try to apply that to a cool data set, make it more interesting. And then we start to get into more hybrid stuff. Diffusion models are, I guess not hybrid, but their math is super interesting, and they're just cool. And they're really good at spatiotemporal data. And that's it. So somewhere around, where is it? Right here, mid-March, we'll talk about the final project. And have you, and I'll bring it up again, you know, periodically, but that's where you'll sort of, at that point, you should kind of know what you want to work on, and then the final project will be the end of the class, and then you do leave. Yep.
I see that there's a principal component analysis of ENSO. Are we going to be doing anything with the MJO at all? The Madden-Julian oscillation, or
If
not
you want
really?
to, I mean, data set global.
Something to consider.
I'm so excited for this class. You have no
Very
idea.
cool. Me too, I hope. So I'm 2 minutes over, so goodbye.
Okay.
No, I'm not like in a rush, but I will try not to keep you over time.
I think, yeah, I'm so excited. Because